So real quick, I just want to go over some of the results that I did for a test of a model that I'm trying to put together. So this is from a GitHub repo called NCP, so Neural Circuit Policy. And basically there are these building blocks of models. They're called LTC and CFC cells. So liquid time constant and closed form continuous neural network cells. And basically when you arrange these cells in a certain way and you add on other sort of modules, then you can actually build like your own custom architecture, right? So the reason why I'm doing that is because basically I'm putting together like a training harness, and this is going to be an alternative to backpropagation. So backpropagation is like the way that most models are being trained, with a combination of that and an optimizer, either stochastic gradient descent or AtomW. And basically I'm using the foundation of a paper that came out like in November 2025. And basically what this does is, well, one of the key things that it does like a bunch of different things, is the fact that it essentially equalizes the cost of training and inference. So usually training costs a lot more expensive. It's a lot more expensive. It takes a lot more time, a lot more resources than inference. But in this paper, it basically equalizes that to where it's just as cheap to pre-train your model from scratch as it is to actually run inference on the model, right? Now, if I remember correctly, this is actually not specifically for all AI models, so it's not for LLMs. I think it is capable of running on LLMs, but it's not really optimized for it. So this technique that equalizes the cost for training and inference is basically optimized for nonlinear RNN, so nonlinear recurrent neural networks, right? And specifically in the paper, he has a kind of neural or a kind of RNN. It's called a GRU, so it's a gated recurrent unit. And the reason why that this is like really interesting is that you can pre-train this in an integer 8 format, right? The reason why that matters is a couple different things. So number one, so the integer 8 sort of data format is the fastest on an NVIDIA H100 chip. And then the second reason is that essentially you can wire in other systems that are also essentially, they're native integer 8 data types into the GRU, and then basically you can take that GRU and then swap that with the GRU within the Dreamer v3 world model, right? So the Dreamer v3 world model is essentially an AI agent that can actually be dropped into a 3D environment, and it can wander around, learn, actually complete tasks autonomously without having the person actually controlling it. It's pretty interesting. However, there are some components to it that are missing, that basically with the release of this specific GRU in that paper from last year, again, you can swap that out into Dreamer v3, and then you can essentially attach a memory module, sort of like a short to medium term memory module via that GRU, because of the fact that both the memory module and the GRU are in an integer 8 format, right? So I have a 7-phase plan that just basically is trying to take the technique, so it's called EGWL, take that technique and then basically turn it into a continuous time evolution system, right? So basically where you have an agent where instead of using backpropagation, where you have a pre-training phase and an inference phase, basically the agent is always on, it's always walking around, and it's training at essentially the same time that it's also doing inference. So it's this constant loop, it's constantly wandering around, basically interacting with its environment, and it's learning rapidly in real time. And again, this also goes back to, well, if you have a system that's learning in real time, then it needs to have a strong memory subsystem, right? And basically this can be achieved via a VSA subsystem, so a vector symbolic architecture, right? Where basically you can encode certain concepts like red, blue, a ball, a car. You can encode concepts within the subsystem, and then that will basically give the agent basically another tool set to perceive the world and overall just make better decisions. So this is just an example of one of the frameworks that I would use within a broader agentic framework. So the VSA subsystem, the vector symbolic architecture. Again, what this is used for is essentially encoding certain concepts within a format, within the integer 8 format. And then from there, the agent will be able to actually get access to this memory subsystem and will be able to, through the pre-training phase and through its interactions through environments, continuously update this VSA subsystem, which will in turn help with its decision-making process. Now, I'm not going to go too much into detail on this right now because it is pretty involved, but just for right now, I want you to keep this in mind that because these core operations of the VSA subsystem, so you have the binding, the unbinding, bundling, these operations are within the integer 8 data format. So when you have that gated recurrent unit, which can be pre-trained in an integer 8 data format, essentially what can happen is, again, through wiring in the VSA subsystem to communicate with the GRU, again, and then you take that GRU and then you swap it out with the gated recurrent unit from Dreamer v3. That's the agent framework. Essentially what you can do is you can now introduce the VSA memory subsystem into a deep RL agentic system. And now it has another tool in its toolkit to essentially perceive the world and make more informed decisions as it's gaining experience. So switching gears, this is going to be the main thing that I'm going to talk about over the next couple of videos. It's going to be the relationship between the NCP and backpropagation and why that this alternative training method actually unlocks some new capabilities with the architecture here, right? So essentially, what the NCP is made up of are cells. So you have LTC and you have CFC cells, right? So you have liquid time constant and you have closed form continuous cells. And basically, when you arrange these cells in a certain kind of way and you add on a couple other modules, you can essentially build your own neural network architecture. And normally, this wouldn't really give rise towards any new capabilities because, again, it's not necessarily about the architecture that's the main bottleneck in what it's actually capable of doing. The actual bottleneck of what these neural networks are actually able to essentially extract information from either video or images, whatever the case may be, it is because of the training method, right? Whether that's backpropagation, evolution strategies, or some other training method, that's going to be the main bottleneck, which decides how these neural networks learn and then what kind of features they're capable of learning, right? So again, over the next couple of videos, I'm just going to go over what the NCP actually is, how it's trained via backpropagation, and then how it's trained via this alternative method and what new capabilities can come from this training method.